So this section's on the law of sine. How many of you have seen that before? One of you? Okay. Couple of you? Okay. This will be a good section then. So the starter question says, which angle is the biggest? So what's the answer to that? Beta. Beta is the biggest. And what's the reason? Okay, it looks obtuse. I'll take that. But in geometry or trigonometry, can you go based on how things look? No. You can't. So it looks like it's obtuse. Okay, but Cameron? Very good. That's the best way to think about this. If you'll notice, I've got a side length of 6, 7, and 10. So the one that's across from the angle beta is the biggest side, so it will have been cut or created by the biggest angle. So beta's got to be the biggest one because it's across from biggest side. The larger the angle is, the larger the side that it's going to create across from it. So there's a theorem in geometry that says something along the lines of this, and this is the way I talk about this theorem when I teach geometry. I say bigger angles cut bigger sides, and what I mean by that is if I've got a big angle like this right here, it cuts out this side from here to here. If I were to shrink this angle down, so if I made it smaller, it would cut out a smaller side. Okay, so the larger the angle is, the larger the side it creates opposite. Okay, so it stands to reason that the opposite side is, we'll call it this, proportional to the side that created it. Now, in this chapter, we start working with triangles that aren't necessarily right triangles. Okay, so we've been doing right triangle trigonometry up until now. This book calls this new type of triangle, it calls an oblique triangle. It calls it, so if we say an oblique triangle, it means none of the angles are right angles. Okay, so it's possible to do some trigonometry on triangles that are not right triangles. We don't have to have that right angle in order to do trigonometry. And this is the first application of something like that, and it's called the law of sines. Okay, and the law of sines is basically based on this idea right here. The bigger the angle is, the larger the side that's created by that angle. Okay? And it works on any triangle, but we do have to be a little bit careful with it. It's a fairly simple idea. So it works like this. The sine of alpha is proportional to side A, and it's in the same proportion as the sine of beta is to side B. And hopefully you remember this. What was that last Greek letter we used? We used alpha, beta, and we can use omega. Okay. Okay. We're gonna use gamma. Gamma looks kind of like that. My gammas look like, so my alphas look like a fish swimming to the left. My gammas look kind of like a fish swimming kind of downward a little bit. Let's see. That's a gamma right there. Okay. It kind of looks like a Y, so kind of like that. But that's the Greek letter gamma, and we'd make that in proportion with side C. So we don't have to use the entire equation. We don't have to use this three-sided equation if you want to think of that. We normally just set up alpha with beta and gamma with alpha, or whatever it happens to be. We look at the sides we're given and the angles that we're given, and we set them up proportionally. Okay, it is possible to use this law and take the entire thing and flip it over. So it's possible to do side A over sine of alpha, proportional to side B over sine of beta, proportional to side C over sine of gamma. Okay, so it's proportional to set it up that, or it's possible to set it up that way. The big idea here would be, well, which one do you use? You use whichever one is convenient, and by convenient, we normally put the unknown variable in the numerator. And that just makes it easier to solve when it's an equation. And we'll look at an example here in just a second. Okay? So if we're looking for an angle, we're normally going to put the angle on the top. If we're looking for a side, we're normally going to put the sides on the top. Okay? So normally we like the unknown variable in the numerator. Okay? So Let's take a look at this first example. This is one that's very similar to the first 4 or 5 problems in the textbook. So it says we've got this angle right here that's 105, this angle right here that's 40 degrees, and it says solve the triangle. Let's see. Yep. Yeah, we're given an angle, angle, and a side. Angle, angle, and a side. So if you're given two angles, you automatically know the third one, don't you? So if this is 105 and this is 40, I've got 145 altogether. What's the measure of, this would be angle A on the way this is written? 35 degrees, okay? So angle A, the measure of angle A is going to be 35 degrees, okay? So that's one of the unknown pieces here, okay? So they really gave us all 3 angles. Okay, now if we're going to solve this, I've got all 3 angles, now I need to find the other sides. And you'll notice that I'm only given one side. Okay, this side right here. Side C is 20, but I don't have side A and I don't have side B. So here's what I'm going to do. I'm going to say I don't know A, but I do know that the sine of A, which is 35 degrees, that's just a number. And I do know that that's got to be proportional to, if this is the side over the angle that created it, let's do this side of 20 over the angle that created it, sine of 105. And then all I need to do is throw this into a calculator, make sure I'm in degree mode, and I'm all set. So this would be A equals, I'm going to multiply both sides by the sine of 35, so this is going to be 20 sine 35 over sine of 105. Now, just like always, kind of take a guess at what's going on here. Okay, this is the biggest angle. That's going to be the biggest side. This is 35 degrees. This is 40 degrees. So when I plug this into the calculator, we're expecting an answer that is bigger or smaller than 20. It's going to be smaller, right? Okay, because these other angles are smaller, they're going to create smaller sides, right? Okay, a lot smaller or a little bit smaller? Yeah, quite a bit smaller, okay? So when you type that into your calculator, again, making sure you're in degree mode, anybody got that? What'd you get? $11.87. Okay, and we'll round to the nearest tenth here. So 11.9, is that pretty close? Okay, so we're going to call this one 11.9. Now, in comparison with the last missing side, so this side over here, when I solve for this one, okay, now I could do this. I could set this up and I could say, all right, 11.9 over the sine of 35 is equal to, let's put B over the sine of 40 degrees. I could do that. Why would that be a bad idea? Yes?
Because 11.9 is an exact rounded.
Very good. We wouldn't want to use a rounded answer to produce another answer, okay? So although 11.9 is a perfectly good answer for that side, we shouldn't use that again because that's going to compound the error. What we should do is like we did on this one, let's use the sides where we know exactly what they are. So I'm going to put 20 up here, and I'm going to put the sine of 105 right here. Now, when I find side B, B is going to be equal to 20 times the sine of 40 over the sine of 105, which if you think about it on your calculator, should already be set for that. Am I looking for an answer that's going to be bigger or smaller than 11.9? Bigger. A lot bigger or a little bit bigger? Just a little bit bigger because this one was 35, this is 40. Those two sides should be roughly the same with this one being just a little bit bigger. And what do we end up with here, Logan? 13.3. Can anybody confirm that? Okay, looks like we're good there. So I've got 13.3 over here. And again, remember, they gave us 3 pieces of information. They gave us 105 and 40 and 20, and we went through and we found the other 2 missing sides, and the other missing angle. Okay? So we've solved that. Not a right triangle, but we still use trigonometry in order to find that. And again, this is called the law of sines, and it basically is the angle is proportional to the side that creates it. The bigger the angle is, the bigger the side that it's going to create. Okay, any questions? Okay, all right. Let's take a look at this one. This one's a little bit different. Okay, the one up above was they gave us an angle, and a side. This one right here, I've got alpha is 28, side C is 8.2, and beta is 66. Angle, side, angle? Okay. Remember, the way you say those is important. They gave us an angle, and a side. Okay, that's the order that they gave them to us in. If this is alpha is 28, side C is 8.2, and beta is 66. Remember, so if I think about it this way, if this is alpha, this is beta, and this is gamma, side C would be in between there. So they gave us this angle, this side, and that angle. So they gave us angle, side, angle. There we go. Why is that still good news if we have to solve this? Yeah, you can find the third angle. If they give you two angles, you've automatically got the third one, okay? So what I would do on this one is I would draw this roughly to scale. So I'm going to draw a horizontal side like this. Whoops. Okay. So I'm going to draw a horizontal side like this. I'm going to draw 28 degrees. So that's a pretty small angle. And then 66 degrees. That's a fairly large angle. Okay. So it's going to look something like this. And I've got 28 degrees for this one and side A across from it. I've got 8.2 for this one, and that would be angle gamma, or we could call that angle C if we wanted to. And then beta is 66 degrees, so this across from it is going to be side B. So gamma is pretty easy to find. Let's go ahead and find gamma. We're going to add those up. Subtract from 180. So if we put those together, is that 94? Is that right? So what's gamma? 86. Thank you very much. Toughest math problem of the day so far. Okay. And then would you go ahead and find side B or side A? I don't care which. 3.85 for A? Is that right? Okay. So 3.85. And if you haven't noticed this, okay, remember on your calculator, you'll notice that this structure right here, 8.2 times the sine of 28 over the sine of 86, okay, that's what will give us A. This looks exactly the same, so the only thing I need to change is the size of that angle right there, okay? Or let's see, I wrote down the wrong one, didn't I? Should be 66, there we go, okay? So I'm just going to recall that, and the only thing I need to edit here is just, I'm going to make the 28 a 66, and I end up with 7.5, okay? Does that match with what we'd expect? 3.85 here, I'll call that 3.9, and this one over here, whoops, other way around. Yeah, A was 3.9, and this one is 7.5, okay? And that should match up because this is the smallest angle, that should be the smallest side. Medium angle, that should be the medium side. This is the largest angle, that should be the largest side. Okay, any questions? Okay, pretty easy? Okay, take a look at the next one. We talk about something called the ambiguous case with the law of sines. The law of sines is pretty easy to work with once you get used to it. Most people like the law of sines. In fact, they sometimes use it even when they should be using something else. Okay? What does the word ambiguous mean? Anybody know? If I said something that was ambiguous, I'd be saying something that was unclear. Could have multiple interpretations. All right? So if we're given an angle and a side and another side, okay? So an angle, a side, and another side. The nice thing about these two examples right here was, this was angle, angle, side. If you get two angles, you've automatically got the third one, so you've only got two missing sides to find. Or angle, side, angle. Again, you've got that third angle. You've only got two more missing sides to find. This one's a little bit different. If you're given an angle, a side, and another side, you have to be very, very careful. Okay? Why do you have to be careful? What's the abbreviation for that one? Okay, now we'll get the giggles out right now. Okay? Do they ever write that in a geometry textbook? No. In fact, if you have your textbook open, you'll see that they always do this side angle. Okay? I pointed out that you could spell it that way because if you see an angle, a side, and a side, think of what the abbreviation is, and that'll cause you to, there's something wrong here. I better be really careful with this. Okay? And it's because there are so many different ways this can be interpreted. We can have no triangles. Okay? We can have one right triangle. We can have two triangles out of this case. Or we can have one triangle. It might be an acute triangle. It might be an obtuse triangle. It's really hard to tell based off the information. You've got to actually run through and do the work. So we're going to look at this and we're going to figure out why is this the ambiguous case. Okay? So when we say I've got an angle, a side, and a side, remember we pointed out before that the order that those are given is important. So we know the size of this angle, we know the size of this side right here, and we know the size of this side across from it. We know how big each one of those are. Now you'll notice that we have a very long horizontal side right here. This angle is fixed, this side is fixed, and then this angle right here, this side right here is kind of just swaying in the wind. So kind of think of this as a board right here, and then I've got a hinge right there that allows this to swing back and forth. Okay? No matter how much I swing that back and forth, is this side long enough to come down here and hit this other side and make a triangle? It's not. Okay? Side A is too short. And the reason it's too short is you'll notice that on every one of these I've got this H on here. This is how high it is from this point up here down to that one right there. Okay? And if that is less than, if side A is less than H, there's no way we can make a triangle. So figuring out how far it is from here to here is really important because we're going to use this side and make a comparison with that height, that H. You'll notice on this one right here, again, this angle is fixed, this side is fixed, this side A right now is exactly long enough. Okay? So A is just right. And the reason it's just right is A is exactly equal to that height that we're going to find. So no triangle if it's too short. If it's the exact same as the height, then we only have one triangle. And the reason we only have one triangle is if I were to swing that up here or over here, it's not long enough to hit this side anymore. It's just barely long enough. It hangs down, it just touches right there, and that's it. If you swing it one way or the other, it's not going to touch anymore. Okay? So no triangle here, one right triangle here. And then this is the more difficult case. This is the one that we don't really like running into. Okay, because there are two different triangles that could be formed using this information. Okay, so one thing that could happen is, let's say that A is longer than H, but it's still smaller than B. One thing we could do is we could swing this side right here out this direction, and we could make a triangle like this, or we could swing it in this direction and make a triangle like that. Okay, so A is long enough to make one triangle with an acute base angle. Which one is this? Is it picture 1 or picture 2? Okay, this right here is acute. It's that picture right there. Okay, if I swing it in here, notice what happens to this angle beta right here. It becomes obtuse. Okay? And the reason we can have two different ones is because A is bigger than H, but it's smaller than B. And you might think, well, it's always been shorter than B. It's shorter than B here. It's shorter than B here. It's still shorter than B here. Let's take a look at what happens if A is bigger. Okay? If A is bigger than B, then we only have one triangle. And the only option here is this. Okay, so say it's this long. If I swung it over here, some people will say, well, yeah, you could make a triangle like this. Okay, that's not the right idea. The only way that you could swing it to make a triangle is by swinging it out here. Can somebody tell me what's wrong with swinging it this direction? Why is this triangle right here, let me highlight it, why is that triangle not okay? Brandon? You could think of it as negative, or remember, isn't alpha inside the triangle? Is alpha inside the triangle here? It's not. So really, in order to make this triangle, if you were going to swing it this way, the only way you'd be able to do that is to swing it all the way around until it lands right there. Okay, to keep angle alpha inside there. Okay, so here A was too short, here A is too long. Okay, and the only way that you can swing it is that one direction right there. Okay, any questions? Okay, so if you have, now you're going to have problems that, example 1 and example 2, those were pretty easy, weren't they? Angle, sides, angle, side, angle, piece of cake. No problem with those. If you end up with angle, side, side, here's what you want to do. The first thing you want to do is you want to draw a long horizontal side. Long horizontal line. So let's go ahead and do that here. I'm going to draw a long horizontal line. Draw the angle, okay? And usually it's acute, okay? And I've got a star by that, okay? Draw the acute angle and the adjacent side roughly to scale. So that's an acute angle. Keep track of that. That's important that it's acute. And the adjacent side. Which two of these are, or which one of these is the adjacent side? It's B, okay? Because remember, if this is angle alpha, side A is across from it, all right? So I'm going to draw something that's roughly 41 degrees. So I would say 41 degrees is about like this. So I'm going to put 41 degrees right there. And this side right here is 5.4. Any questions? Okay. Find out how long H would need to be in order to make a right triangle. So drop a line straight down here and figure out what H is. Figure out how tall that is. Now, how would you do that? Can't use the Pythagorean theorem because you've only got one. Yeah, you're going to use the sine. Okay, this is a right triangle. Okay, so I'm going to say the sine of 41 degrees is equal to h over 5.4. So if you think about it, I'm going to multiply both sides by 5.4. Okay, h is always going to be that side, the hypotenuse, if you want to think of it that way, times the sine of 41 degrees, times the sine of that acute angle right there. Okay, and on this problem, what is h? 3.54. So in order to go from here down to here, both of these are drawn roughly to scale, I've got to have something that's 3.54, call it inches or whatever. Okay, how long is A? 3.3. That means it hangs down to scale roughly about right there. It is just swinging in the wind. Do I have a triangle? Don't have a triangle. Okay? No triangle. Okay, we love it when that happens because we're done with our work right there. And what we did there is we compared the sides to see how many triangles you have, if any. When we compared, this isn't even long enough to make one triangle, so we have no triangles at all. Okay? And just one last word of caution, make sure that there's really no substitute for thinking about how big the angles are, how big the sides are that they create, and stuff like that. Okay? So let's take a look at this one right here. Please do these the same every time. First of all, check and see what we've got. I've got an angle and a side and a side. And if I put these in order, this is angle beta, this is side B, and this is side C. So this is the angle, this is the side, and that's the other side. So it's this one, then that one. Okay? Because remember, B is going to be across from angle beta. So I'm going to draw a long horizontal side. 38 degrees is roughly about right there. So we'll call that 38 degrees. Side C is the one that's next to it. That's going to be 5.9. And then I want to figure out how tall this is. I want to figure out what h is. Remember what I said a second ago. If you want to set up this little equation, go right ahead. But h is always going to be that potential hypotenuse, we'll call it, times the sine of that acute angle right there. So that's 38 degrees right there. And what is 5.9 times the sine of 38? What is it? 3.6. Okay, are we expecting a fairly small height right here? It's going to be a lot smaller than 5.9, right? Because that's a pretty small angle, 38 degrees. Okay. How long is this? Whoops. How long is this in comparison? It's huge, isn't it? Okay. Way down here. In fact, isn't it bigger than this right here? So is there any way I could swing it over here and keep 38 degrees inside the triangle? Nope. Okay. Got to swing it out this way. And we're going to have a triangle that looks something like this. So I don't need to worry about the 3.6 anymore. I can write this side is 6.4. Now remember, this is beta, this is side B, this is side C, so that's going to be gamma, and this is going to be alpha, and this is going to be side A. Okay, now listen very carefully. Is this angle out here acute or obtuse? It's going to be acute, isn't it? Okay? Because if that was a 90-degree angle, if I swing it out there, it just gets smaller and smaller. The law of sines works really well if you're trying to find an acute angle. It doesn't work very well if you're trying to find an obtuse angle, and we're going to figure out why in just a second, but keep that in mind. This is the one you want to find first. Don't set it up to find alpha, because that's obtuse. You want to find the acute angle first. So let's go ahead and find that. I'm going to put the sine of gamma over 6.4 should equal, and what do I put over here? Whoops, 5.9. Thanks. Okay, and then what do I put over here? Sine of 38 degrees over 6.4. So again, I've got the angle and the corresponding side matched up. Angle, corresponding side matched up. Angle right here, corresponding side over there. So if I set this up to solve for gamma, I've got 5.9 sine of 38 degrees over 6.4. How do I finish solving for gamma? Sine inverse. So gamma is going to equal the sine inverse of 5.9 times the sine of 38 over 6.4. Any questions? Yeah. Okay, everybody watch, please. Okay, this is a great question. Okay, if I put beta right here, that means side B goes across from it, right? Okay. Side C, I'm always drawing this horizontal line right here. It's not going to be the one that I know. I always know this angle, this side, and this side right here. So I've got the angle of 38. That's angle beta, so side B is going to be across from it. So that's got to be 6.4. That means this one has to be right next to it. Okay, I've always got angle, side, side. Lynn's question is a great question because if you don't set it up the same way every single time, you're going to sit there and wonder, well, wait a minute, which one do I put where? Okay, you're always going to put the acute angle here. This side right here is one we don't know yet. So it's always angle, side we know, side we know. It always goes in that order. Does that work? Okay. And what did we get for gamma? What is it? 34.58 degrees, right? So this angle right here, 34.58. Any questions? Okay. Once I have this angle, by the way, was I expecting that? The answer is yes for a couple of reasons. Didn't we say it would be acute? Yes. Take a look at this side right here, 6.4. It's across from an angle of 38. This is 5.9. That's a little bit smaller than this, so shouldn't we expect an angle that's a little bit smaller than 38? Does that make sense? Okay. Now, once I have an angle here and an angle here, do I need to use the law of sines to find alpha? No. So for alpha, we're going to do 180 minus 38 minus 34.58. And can somebody tell me what alpha is? 107.42. Okay? Now, there's no way to get around using a rounded answer on these. So you're going to have to use a rounded answer to some degree. I like using, storing the answer in your calculator and using that much decimal approximation. Okay? Making it as accurate as you possibly can. Let's just set up something that would find the last one. I can do A over the sine of 107.42 should be equal to, what one should I use over here? Should I use the 5.9 and the 34.58, or should I use the 6.4 and the 38? Yeah, put the 6.4 here and the sine of 38 over here, because then I'm only using one rounded answer, not several rounded answers. That's going to be more accurate, okay? You can go ahead and find that and figure out what A is. And then we're going to look at the next example. What'd you get? I see people writing, nobody willing to tell us what they got. Are we expecting a pretty big side?
Yes.
We are. It's got to be bigger than the two of these, right? Quite a bit bigger. What'd you get? 9.9? Okay, 9.9. Okay, any questions? Okay, Let's take a look at the number 5, and we'll briefly look at number 6. We're not going to be able to finish these today, but this will at least give you enough that you can get started. Okay, let's take a look at this one. Angle alpha, 41.2 degrees. So I'm going to draw that about right here, 41.2 degrees. Side B and side A. Side A has got to be across from that. That's got to be over here. That's got to be the 8.1. And if you have to draw something in like this, go ahead. This is 10.6. Figure out what that is. Figure out that height. Remember, that height is always going to be what would be the hypotenuse, 10.6, times the sine of that angle, so 41.2. And when you type that in, what is 10.6 times the sine of 41.2? 6.98. Now let's take a good look here. There's the angle we used. There's what would be the hypotenuse, that one that's right next in line. This is the one across from it, and it is 8.1. Is it long enough to make a triangle? Yes, it is. Is it long enough to swing both directions? Okay, it's not longer than 10.6, so we're going to have two triangles. So this one is a pain in the butt. Please watch. Okay, I want you to find this one. Always draw this one first. Always swing it out here first. So this is going to be 41.2. This is going to be 10.6, and this is going to be 8.1. And we're going to find, if this was B, then that's beta right there. Is beta going to be obtuse or acute? It's going to be acute. Okay? Let's go ahead and find that. Sine of beta over 10.6 should be equal to 8.1 over the sine of 41.2 times both sides by 10.6. Oops, I've got that backwards, don't I? Got that upside down. Sine of 41.2 over 8.1. It's Monday, right? Good thing. I'll use that excuse all week. Okay, what'd you get? Nathan, what'd you get?
I got 59.54.
59.54. Sound about right? 59.54. If this is 41.2, and that side's 8, and this is 10.6, we're expecting this to be a little bit bigger, 59.54. Okay? Now, everybody watch, please, because this is the important part. If I swing this out here, I get an acute angle. If I swing it in here, what type of angle is this right here?
Obtuse.
It's obtuse. Stop and think for just a second. When you're solving these using sine inverse, what is the range for sine inverse? What's the range for sine inverse? Negative 90 to 90, right? And the only angles that would make any sense are 0 to 90. So can you use the law of sines to get an obtuse answer? Nope. Okay? You have to get it indirectly. So here's what we do. If this one right here is 59.54, this one over here has to be 59.94, and I'm going to zoom in on this right here. If that's 59.54, how big is this one over here? Or how would you figure it out? 180 minus that, okay? So here's what I draw for the second one. The second one looks like this. This is going to be 41.2. This is going to be 10.6. This is going to be 8.1. This is going to be 180 minus that one right there. So 180 minus 59.54. And that one's going to be 120.46. Okay? And then could you finish it off and find gamma and side C on this one and gamma and side C on this one? Okay? The last thing I want to look at really quickly is take a look at this. If you drew this roughly to scale, stop and think about this. If this is 130, okay, this is gamma, and A is right here, so A is next to it. That would be 10. Is there any way that this side could be 8? No way. Not possible. Okay? So we'd have no triangle on that one. $130, that's 10, that's 12. Is that possible? It is possible because that's the largest angle. That's going to be the longest side. This one over here is going to be pretty tiny though. Okay? Do I get this triangle, or is it possible to have two triangles with these measurements right here? Only one. Can somebody tell me why? Yeah. It's a lot longer, and it corresponds to an obtuse angle. Don't both of these have to be acute? So when you use the law of sines, it's only going to give you one answer. Okay, you can get started on the assignment. I am going to finish these problems, and we'll look at that application tomorrow.